Hello! Today we are going to talk about analog magnetic audio recording. This is an obsolete technology, but it is part of the heritage of modern electronics, and we still record digital information magnetically, especially on hard disks. And who knows, you may have an opportunity to work on some vintage equipment sometime that is becoming a popular thing. So let's go ahead and start learning about how this all began. And don't forget that this is part of my free course at Vocademy that you can take for free at vocademy.net. So analog audio recording developed somewhat in parallel to radio broadcasting. So the idea is, let's just take a look at how sound goes into an electronic system. I'm going to pretend that my pen here is a microphone. And as I talk, there's a diaphragm in there that vibrates back and forth. And as the sound pressure waves from my mouth hit it, as the pressure goes up, it'll cause the diaphragm to move away from me. And as the pressure goes down, it'll cause the diaphragm to move towards me. And it will move in a way analogous to the sound waves, which if we look at as a single frequency, of course, would look something like this. We get a sine wave, where as the sound pressure goes up, we get a higher voltage. As the sound pressure goes down, we get a lower voltage. And this is used in radio, of course, to modulate the radio transmission, which we will talk about down the road in communications electronics. But the idea was, is there some way we could magnetically record this? And the early days of magnetic recording, the obvious way to do it was on steel wire. Because steel is magnetic, you can draw it into a thin wire, put it on spools, and somehow run that wire through a magnetic device and actually record this signal where we have stronger and stronger magnetism, weakens down, reverses polarity, gets stronger and then gets weaker. And so the idea is that we have a mechanism that transports that wire. So here's a spool of wire here and another spool of wire here, with motors to move those spools, and in the middle is a recording and playback head, as it's called. So in here we have we'll just draw it like this, a broken loop of iron which has wire wrapped around it. And of course, as we put current through this wire, what do we get? A magnetic field. That magnetic field will be concentrated in the iron and span this gap here, and of course, since we have a gap, that magnetic field is going to escape the gap a little bit. All we need to do is get that wire to go across that gap, and that's going to expose the wire to the magnetic field and magnetize the wire, assuming that it's a proper alloy that will hold its magnetism once it's passed through a magnetic field. So we simply send our signal into there, and as the current gets higher, we get a stronger magnetic field here. As the current gets lower, that gets weaker. And all that time we are moving this tape by. So we're recording higher magnetic fields, weaker and weaker, and then we reverse the polarity, and then we get stronger and stronger and weaker and weaker. So we have these strong and weak magnetic domains on this wire that are one polarity and then reverse polarity. And so it's an analog of this electric signal on that wire. And then to play back, we just spool it back on the original reel and run it back by. And now as those magnetic fields pass by this head, it's going to transfer some of that magnetism over to the coil. And out will come a rather weak signal that we can send through an amplifier and make bigger, and eventually send to a speaker and hear what we had on the wire. It's a very simple idea. Of course, it got more complicated than that, but that's the gist of magnetic recording. So let's look at some of the problems they encountered doing that and how that led to modern recording as we know it now. So the first problem was that the sound, although usable, was somewhat distorted. And let's figure out why that was distorted. So what I'm going to do now is draw a graph of our magnetism versus our current. So our horizontal line represents our current. This is current going through that recording head that I mentioned before. And the vertical line will represent our magnetism. So this will be positive current, meaning the current is going one way. It doesn't really matter which way, but we'll start with one direction, then the other. So the current's going one direction, that's our positive current. Going the other direction, that's our negative current. And then the magnetism is going to be what direction the magnetic domains in that metal are magnetized. Are they magnetized north and south this way or north and south that way? So we go north to south and then south to north. And so once again, the vertical axis is our magnetism, the horizontal axis is our current. So as we increase the current, we'll make it positive current. As we increase that current, we're going to get more and more magnetism. Until we get to a certain point, we'll do that right about here, it's going to drop off to a point where increasing the current no longer increases the amount of magnetism. So that's called saturation. And this has the same problems as saturation in a transistor circuit. Remember, in a transistor circuit, we have our sine wave going in, and if we saturate the circuit, in other words, we get to the point where increasing the base current of the transistor no longer increases the collector current, and what we're going to do is end up chopping these off. If you don't remember about this, be sure to review the class on small signal amplifiers. And so by saturating that, we end up clipping off the tops and bottoms of our sine wave, either one or both. And when it comes to magnetic recording, we get the same thing. If we get into saturation, well, increasing the current no longer increases the magnetism, so we can't record the higher peaks, and so we get exactly the same thing, a chopping off of the peaks, which introduces harmonic distortion, basically a lot of odd harmonics, and sounds terrible. So we want to stay out of that area for sure. And we have the same thing going the opposite direction. So when we reverse the polarity of the current, we end up reversing the polarity of the magnetism, and does exactly the same thing. So there's the curve of current versus magnetism going onto the magnetic medium, wire or tape or whatever we are recording on. But then when we remove the current, that magnetism is going to drop. So we're increasing the current. Let's say we put the current right here, and at that point we remove the current or decrease the current. You don't have to completely remove the current immediately, but as the current goes down, the magnetism is going to go down, and when the current is completely gone, so now we're at zero current, we're going to have some residual magnetism. So however big the magnetic field becomes and how much we magnetize that medium, when we take the current away, that magnetism is going to drop a little, but eventually settle on a point where it remains magnetized even once the current is gone. So as that tape is going by the head, so here's the head, or the wire is going by the head, the wire, the tape, or whatever it is, it gets magnetized, but then it moves away from that magnetic field and remains magnetized according to what the maximum power of that magnetic field caused by the current is in the head. Now the problem is this curve isn't as clean as I've drawn it here, and that might be a little confusing if you look this up and look at the hysteresis curves and such. If you don't get the right reading materials, like I got some from 3M, which gets down into the real details, this isn't quite as clean as it looks right here. What we have is what's called the transfer curve, which tells us how much magnetism we have left on the tape depending on how much current we had put through it. And it's not quite so clean. It kind of goes, let's see if I can redraw this a little without making too much of a mess. So it's going to go down, and then it's going to do something like, it's not dramatic enough. That's better. Let's see, that's good enough. Okay, it's going to do something like this at the bottom. So our current to magnetism is going to follow a curve like that. So what's that problem give us? We have some non-linearity down here, which is going to cause our sine wave, which starts out like this, to get kind of messed up in this area. So we're going to end up with a sine wave. I'll just try to redraw it. Sine wave that looks sort of like, So now we're introducing other harmonics. I don't know if they're even, odd, or both, or whatever, but we're introducing more distortion, and that's certainly not going to sound good. So we need to somehow mitigate this area where the magnetism and the current don't quite go linearly. So we have a region up in here and in here where it's fairly linear. So increasing the current increases the residual magnetism just right so that we don't get this distortion. What it does, it's hard to draw, but it means that our residual magnetism is not going to be evenly distributed according to our currents once we get down in this area here. So we want to stay up in this area, in that area of the current magnetic curve, so that we don't have distortion. So how do we do that? Well, the first experiments done with that were with a DC bias. Instead of having our signal, which I will redraw over here, this may sound familiar. In fact, it should sound familiar if you've watched the video and read the material on small signal amplifiers. What we're going to do is, instead of having our sine wave go positive and negative with our 0 here, so that would be in the electronics 0 volts. It's going to go positive volts to 0 to negative volts. What we're going to do is we're going to mix in some direct current, and basically that's going to, well, I'll just redraw that. Mix in some direct current. Be sure to watch the video on small signal amplifiers to understand this. We're going to mix in some direct current. So there's our sine wave. There's 0 volts. So we've pushed that up by mixing in direct current. And so now this goes to some peak voltage. This goes to some smaller voltage. So let's say it goes up to 10, down to 2, up to 10, down to 2 with a 8 volt swing in there. So we're getting that where it doesn't cross 0. And so this is what they tried in early wire recording to get it out of the distortion area. So now we are only working in this area here. Higher magnetism, lower magnetism, higher magnetism, lower magnetism. Then the magnetism stays the same direction on the tape or the wire. And as that goes by the hedge, our magnetic field is going to get stronger, weaker, and basically cause a current coming out of here that's stronger and weaker and stronger and weaker. And we can send that through a capacitor to pull it down to centering on 0 volts again. So fairly simple idea, except there's a problem with the medium we're recording on. As we magnetize the medium, we have these tiny molecular-sized magnetic domains that are magnetized, and they're strongly magnetized, and they're going by this head and basically causing tiny bursts of magnetic energy. And we don't want that, and those tiny bursts of magnetic energy coming at random come out as a hissing sound on the playback. And this is because all of our magnetized domains are fairly strongly magnetized up in this area. If we could somehow move this down to here, we would have much less noise because the domains would not be as strongly magnetized. So as they go by, we get little bursts as these domains go by, which comes out as hiss. So how do we get rid of that? Well, there were a couple of times in the early history, in the early 1900s, where people experimented with AC bias instead of DC bias. And those kind of went by the wayside. People forgot about them. And how successful they were, I don't know. But in the 1940s, I don't remember where this was or who did it, but I'll put a name up here of the person who rediscovered the idea of AC bias. Working in the laboratory developing audio recording equipment, the amplifier that was sending the signal to the head broke into oscillation, a very high frequency oscillation. I don't know what frequency that was, but I'm assuming it was ultrasonic, so it was something above 20 kilohertz. And lo and behold, that oscillation reduced the noise. So what was going on? I'm going to redraw this. So here is our graph. Remember, this is current, magnetism, and let's draw our curve here. So it's going to go something like that. There we go. And so here comes in our ultrasonic signal, very high speed sine wave. So what we had was an additive mixing of the two signals. Let's see if I can draw it up here. So here's our high frequency sine wave mixed with our audio. So we ended up with a curve that was going up and down like this. So if they adjusted it just right, let's be try to redraw it right here. Up a little, down a little, back up a little, so that the peaks of these never drop into the nonlinear area here. So the peaks are carrying the audio signal. Now, this is a very high frequency signal, and it's beyond the frequency that can be recorded on the tape. So Before I go on, I want to explain something about erasing tape because I think this will help us understand why this is an advantage. So I want to erase some tape. So what I have here is called a bulk tape eraser. I still have this. In fact, I bought this fairly recently because I have other uses for it. I had one before and it burned out. But what this is, it's just got a power cord, this plugs into the wall, a little momentary contact switch, and that just runs current through a big coil of wire here with a heavy iron core that's open at the bottom, so I have a strong magnetic field out the bottom here. And so to erase tape, I take like a whole reel of tape, or later on floppy disks, whatever I was trying to erase, a compact cassette, whatever would work. And I put this against that, and I move it around to get that magnetic field everywhere, so that it just scrambles up those domains, doing that while I'm holding this button, of course. And then I let go, well, it stayed magnetized one way or the other. So that's going to add a DC bias to my tapes. What did that do before? It caused noise to have those magnetized domains on the tape. So to make sure that they weren't there, after I'm really through, I slowly move them apart. So now the magnetized domains are switching back and forth, smaller and smaller and smaller and smaller, until I get it as far away as I reasonably can, like about 3 or 4 feet. Now those domains are just flipping very small, almost no magnetism at all. Then I release the button, and now it's completely demagnetized. So you want to send that AC signal into there that flips the domains back and forth, and as you move it away, magnetism's less and less and less until I get it far enough away that the magnetism's almost nothing. And so now I'm back to this point here in the middle with no current, no magnetism. So that's about erasing tapes. And by the way, I said I have other uses for this. Let's say I drop a bolt in the grass while I'm working on something. What can I do? I can't find it. Take this out there, picks it right up. I also used it once to get metal shards out of a can of fruit drink. Opened it up and some chips of metal went into the fruit drink, took this in there and just picked them right out of there. So I keep this handy because even though I haven't had use for it as far as what it's designed for many years, I still have an occasional use for it, so I keep it around. So, knowing that to demagnetize something, we want to get those magnetic domains flipping back and forth tinier and tinier and tinier to get us back to this point here. Well, that's basically what's going on here. As this goes across, it's magnetizing it a lot, but as that moves away in the head, so here's our recording head here, and our wire or tape or whatever goes by there, as it moves away, we've got that alternating signal. It basically demagnetizes until we get to 0 as we move away. So we're basically running a demagnetizer across this, but because of this shift, as we're here, it doesn't quite go down to 0. It ends up being shifted a little bit to the one direction of magnetism. And as we get down here, because this is offset, it gets shifted to the other direction of magnetism. So we end up with what's actually on the tape does not follow this transfer curve, but actually follows, if we draw the whole thing, let me draw this in red just to make it stand out. What's left with the AC bias is, if we follow the same curve, does not follow the transfer curve, but ends up that if we're like right here, where we get equal amounts of magnetization on either side of the 0 line, it's going to be completely demagnetized. But if we're offset a little bit, it leaves a little residual. And notice there's no distortion. So the bias signal is too high of a frequency to be left on the tape, but because we are skewing it with this audio signal on top, as that bias signal basically erases the tape by making those magnetic domains smaller and smaller, it's offset by the audio signal such that we end up with a curve that does not follow the transfer curve, which is what we would get if we did not have the bias on there. So that is the purpose of AC bias in recording. So that was rediscovered by accident, and so they developed on that. And so what we do is when we are recording, we send an ultrasonic signal. This might be anywhere from 40 kilohertz to 150 kilohertz. Seems like 100 kilohertz is very common. There's no way the tape can record such a high frequency. We'll talk about frequency and speeds and tape gaps in just a moment. But since that can't be recorded, it basically erases the tape. But once again, we get a little bit of an offset from this audio signal that's put on top of it that causes our erasure to end up following a nice linear curve. So as long as we keep our peaks in this area, there's just the peaks in those two areas there. So the peaks are going there and there and there and there, and we stay in between with those peaks. Keep the peaks in between. Didn't quite draw it right, did I? Well, anyway, we keep the peaks in between these two lines. Not worried about what goes on between there. We'll end up with a nice linear recording on the tape. Hope that makes sense. It's a little bit hard to follow, but that's the idea of adding the AC to the DC. It erases the tape, but leaves a little residual because of the offset, and so we end up with a nice linear curve as long as we stay below this saturation part of that curve. So this is called the transfer curve, which is what would happen without the AC bias. But with the AC bias, we get this red line that follows a nice linear curve instead of the transfer curve. Hope that makes sense. So now I have explained why we have AC bias on the tape. Remember DC bias, we just kept it up in here, but because we had that tape strongly magnetized, those domains were going by making a hissing sound. Now we're still going to get that hissing when we have a strong signal, but if we have a weak signal, we're not going to be magnetizing them as strongly, and so we don't get that hiss because it's the strongly magnetized domains going by the head that cause that hissing sound. So we end up with, when the music is quiet, the domains are not as strongly magnetized, and so we don't hear the hiss. And of course, when the music's loud, it overwhelms the hiss anyway. So that's the purpose of the AC bias. So the wire recording, we basically had a steel wire. Different alloys may have given us different qualities that we could control, but now we've moved on to tape. So what is tape? Modern audio tape is going to be a base, I'll just draw it as a chunk here, of, I don't know if I'm using any other material other than polyester. Maybe in the early days they used something different, maybe acetate, maybe film stock, who knows what. But modern tape is made with polyester. You may know that as mylar. So DuPont calls polyester sheet mylar. Everybody else calls it polyester. Now there's one problem with it, which was a big problem in the early days. If you pull on that, it's going to stretch, and that causes it to curl. And I remember in the early days of audio tape, you'd be rewinding the tape and it would snag and it would stretch it and it would ruin the tape. It'd just stretch it out and it would curl in on itself and it was done. So they started pre-stretching the polyester before they made it into tape. So it's a big deal in the early 70s that you bought an open reel of tape and it said pre-stretched. So you knew it wouldn't get ruined if you put too much force on it. So we have this pre-stretched polyester. It's cut into very long tapes. I think a minimum length is going to be like about 1,200 feet. I think they measured it in feet. It's going to be 1,200 feet. They measured it in feet because, of course, all this stuff came from America, where we don't use the metric system. Well, we kind of are now, but back in the day, everything was imperial, and so I'll be using a lot of imperial units here. You'll have to convert that to metric, but here we go. So now on top of this polyester sheet, we put a very thin layer of, originally, just iron oxide, which is rust. Finely ground rust, very, very finely ground rust mixed with a binder, basically a glue, and they would bind it on this tape. In fact, I recommend you watch a video from The Secret Life of Machines where they talk about magnetic recording. And they actually take some plain old sticky tape, or Scotch tape as we would call it in America, even though it's not all made by 3M anymore. And they just rub some iron oxide powder, so powdered rust on there. So they had sticky tape and rust. Ran that through an audio recorder and recorded on it. It was marginally effective. It gets distorted and muddy after a while. I think it's because it slipped off the head. They don't seem to realize what went wrong, but it did work. They were able to get a fairly good recording on sticky tape and rust. So you need to watch that. I'll put a link in the description, and of course at vocademy.net in the reading material. There's a link to that video. Very highly recommend you watch that. So we have that iron oxide layer on there, which is magnetizable. So instead of magnetizing wire, we're magnetizing a layer of iron oxide. And this is on tape that can be put on reels, very easily controlled, more compact. And other than that, there's a lot of similarities in the mechanisms for handling this. So the mechanism for handling it, we have the transport, which is what moves the tape or the wire or whatever. Now, one thing about a wire recorder is that the head that recorded on the wire moved back and forth to help evenly move the wire as it spooled onto the take-up reel. That's not necessary on a tape recorder because the tape is flat and it just winds up on itself. So we have the transport, which is going to have the feed reel and the take-up reel, and these are motorized, of course, and this comes off. It may go through a idler arm for a tensioning mechanism, may or may not, and I'll talk more about the heads down the road, but it's going to go across one or more heads and then to the take-up reel going in that direction. This is spooling off in that direction, and it goes by the head, and the head doesn't have to move because it's not trying to spool that wire on the reel evenly. It just spools it on over. So that's the basic transport for the tape. More about what goes on at the heads a little later. So the basic formulation was just iron oxide. You look at older tapes, they're quite brown in color because they're just tape and rust. But they developed better formulations, adding cobalt to it darkened it and also increased the quality of the recording. I don't know if they had to change the bias for cobalt tape or not. I don't think so because there's no settings on a reel-to-reel recorder for old iron oxide or more modern iron cobalt formulations. But they developed better and better formulations as time went by. I know that Maxell had a very good formulation, worked with the regular system though, and had lower noise and better frequency response. So there are different formulations. We'll get into that even in more detail when I get into cassette recording, but we'll just stick to reel-to-reel now because that's the basics. So we've talked about the types of tape. Let's talk about the heads, and we'll talk about the speed of the tape going across it and how that affects the quality of the sound. So let's look at one of the recording heads. Here's a drawing of one here. I'll redraw it down here. Basically, we have some iron with a oversized gap, and there's a coil of wire coming in here that we can feed that, and of course we have the gap there because that's where the magnetic field comes out from between the iron poles there, and as the tape goes across there it magnetizes the iron oxide or whatever formulation we have on that tape. So as we magnetize it, look at the width of this gap I put here. Well, as that tape is moving by, we have an alternating current going in there, and as we're magnetizing it, well, we're magnetizing it strong right here, and then that moves away, but then we're magnetizing weaker, and if it doesn't move away fast enough, let's just like draw the tape here. So we're trying to record a sine wave, let's say, and let's say we're just right there, so we have a very strong domain there, and then we're trying to get weaker and weaker and weaker, let's say down to here, and in between there, well, we have a lot of overlap as that goes. So we need to move that tape by very quickly to reduce that overlap, because our higher frequencies, which take up less space on the tape, let's say we're got a whole bunch of domain changes like that, and the gap is this wide, well, we're trying to magnetize parts of the tape that are much smaller than the gap, and the gap is going to say, no, you're going to magnetize parts of the tape that big. As you can see, the high frequencies just aren't going to record. So one important thing to note and to engineer is how tiny is that gap. We want a very small gap, so shrink that gap, and now we can make tiny, tiny little domains and adequately record the higher frequencies. And of course, though, we can also increase how well that works by just moving the tape faster, because, let me redraw this and make sure that makes sense. So here's the tape zipping by the head. So here's the gap right there. And so if we're trying to record tiny little spots that close together, that gap's not going to cut it. But what if we move the tape faster? Those spots will be further apart. So moving the tape faster gives us better high frequency response. So the speeds of tapes were based on a basic speed of 15 inches per second. You might find some professional equipment that moved 30 inches per second, but that was kind of rare. The standard professional speed was 15 inches per second. For home audio, that was rather rare. I actually modified a reel-to-reel recorder. I had to do 15 inches per second, but it didn't improve the sound quality enough to bother with, so I unmodified it and kept it at the highest speed of 7.5 inches per second. So your typical audio recording reel-to-reel systems had a maximum speed of 7.5 inches per second, and at that speed you got your best high fidelity recording, you got your best high frequencies, which of course carry the brightness and the definitions of your sounds. So you want that tape to go fast in a tiny gap. But what if you are not so interested in high frequency response and you want your tape to last longer? A 1200 foot tape would last about a half an hour at 7.5 inches per second. Well, if you cut that in half to 3 3/4 inches per second, then that tape would last a whole hour. Quality wouldn't be as good, but if you didn't want the quality, you would have a maximum frequency response of maybe 10, 11, 12, perhaps 15 kilohertz, depending on the gap, but not as good as the 20 kilohertz or higher of the higher speed, but trade-off, longer recording, less high frequency response. And if you only needed to record voice for a very long period of time, you could double the time again by going down to 1 7/8 inches per second. And so that would give you 2 hours on a 1200 foot tape, but very, very terrible sound. That would sound kind of muddy, but well enough to hear voice. The tape decks I had a frequency response up to 22 kilohertz at 7.5 inches per second, which was more than adequate. So like I said, I didn't need to keep the 15 inches per second modification on the system. It didn't really work that well anyway, because the take-up reel and speeds were not made for that, and it didn't take up as well as it should have. So it works best at 7.5 inches per second. So that's how your tape speed and your tape head interact. So smaller gaps, be able to get higher frequency because you're trying to record those domains very, very close together at high frequencies. So you make a smaller gap, you can get those domains closer together, or increase the speed. That puts them further apart, so the smaller gap works better at the higher speed. So the smaller your gap or the higher your speed, the better the fidelity of your recording. Now let's take a look at the tape head system that was typical. The simplest would be to have a single head, which was both a record and playback head, and the simplest way to make that is just a simple single coil and a single gap, and you can either record or play back on it, which was not at all uncommon on inexpensive systems. But you could get better quality if you optimized your heads for recording and playback. So a lot of systems, your high-end systems, the ones I had were not super high-end, but they were fairly high quality, had a separate record and playback head. Two advantages to this. One, this one's optimized for playback, this one's optimized for record. Also, you could monitor your tape as you recorded it, so you could actually have your sound come out of the playback as you were recording, and so you could have headphones on, and there's a slight delay, but you could hear if there were problems in real time. So that was another advantage of separate record and playback heads. Now, what if you have a tape that you are recording over an old recording? Now, the best thing to do would be to take that bulk tape eraser and erase the whole tape. But sometimes you might want to record over just part of it, or just don't have a bulk eraser or whatever. All of your tape decks have an erasing mechanism. The simplest, if we go back to the single head, would be to simply have a little permanent magnet on a little arm that pushed up against the tape when you were recording. That would erase the original signal, but what would that do? That would leave a magnetism on the tape like the DC bias. So actually it left a noisy tape, because remember, if we leave those domains magnetized in one direction strongly, we're going to get those domains go by getting pulses of energy, and so we get that tape hiss. And so a permanent magnet to erase, that was extremely cheap recorders. I actually, my first tape recorder I ever had that, but that's really bad. So your better systems would have 3 heads: record head, a playback head, and an erase head. So what did the erase head do? You just simply sent that bias signal to it, and that would erase the tape before it got to the other. So we have that AC on there. As the tape goes by, it gets magnetized, but as it passes by the gap, the magnetization gets less and less and less and less and less, and you end up with an unmagnetized track going by the record head. And so your best decks would have 3 heads. So they're advertised, 3-head deck. So erase, record, and playback. A little more about the heads. You also might find that your heads are advertised as parabolic. So if we have cylindrical heads like these, we required pressure pads, little felt pads on springy arms that pushed the tape against the head. And that's the problem, because that pressure pad becomes unaligned or worn or whatever. If you don't have that tape held tight against the head, we lose that high frequency response. And so that was a perennial problem, always having to replace these pads, cleaning them sometimes. Sometimes I'd have to take a little needle and kind of pick at them to kind of fluff them up a little bit to get the pressure right. They were a pain. But if you don't have the more expensive equipment, which I did not have, you have that pressure pad problem. So some systems had hyperbolic heads. I'm not sure why this geometry did what it did, but the heads were hyperbolic in cross section. And with those hyperbolic heads, you did not need pressure pads. So I never had one with hyperbolic heads. I never had that luxury, but that was something that was advertised. Hyperbolic heads, no pressure pads required. Another thing about the tape transport system I need to mention real quickly is controlling the speed. So here's our reels, our feed reel and our take-up reel. Here's our heads here. Now, a really cheap recorder would just have a motor on the take-up reel and just pull the tape across. But that doesn't control the speed. So as this reel fills up, we're turning the reel the same speed, but the tape is further toward the edge, which has a higher angular velocity. So the tape goes faster and faster as the reel fills. Very cheap recorders might have had that. I had, like my very first tape recorder had that system. But any decent tape recorder is going to have what's called a capstan drive, where they have a metal cylinder, probably somewhere right around there, and then a rubber pinch roller. And when you were playing back a recording, these would come together and pinch the tape and move it at a steady speed across the heads. And then the take-up reel just had a clutch on it, so it took up as necessary rather than being the impetus for moving the tape. And also this had a clutch on it so that it kept a proper amount of tension, or it may have had some electricity going to the rewind motor to give just enough tension so that we have tension on this side, capstan on this side pulling the tape through. And on this side there may have been a tensioning idler dependent on the system, and that pulls the tape to have just the right tension as it goes through the system. So may or may not have existed. Some had a tensioner, some didn't. So that's the probably the last thing I need to say about the transport of the tape. So if we look at the face of the tape, a monaural recorder could take up the whole tape. I've actually never seen one that does that. Every recorder I ever had, even when I was a kid, you could, after recording the tape, you could flip the take-up reel to the feed reel and record again. So you could record 2 tracks. So basically what they do is they offset the recording head such that it only covers half the tape. So when the tape is moving this way, we're recording there, but then when we flip it over, well, if we flip the whole thing over, we find that now the head is over on this half as the tape is going the opposite direction. So we have to kind of flip our minds over. The tape is going this way, this half of the tape is recorded on, but when we flip it over, it flips which side of the tape is being recorded on. So we could actually record 2 tracks on one piece of tape. But then came stereo. And I don't know why they did this scheme, but they did. So your stereo reel-to-reel recorders, once again we look at our tape, and so our heads would be here and here. about like that. So you'd record one track, there's maybe your left track and your right track. I don't remember which was left and right as far as whether it was on the edge or the middle. But we'll say that's the right track and that's the left track. Then what happens when you flip over the tape and run it the opposite direction? Well, then now this head is here. I'll just draw it darker. And this head is now here. So recording the opposite direction, it would record that way. I don't know why they staggered the tracks like this. You know, there would be a little bit of a space that's not recorded. That's called the guard band between the tracks. But the stereo recording in reel-to-reel tapes, the tracks would be interleaved like this. So recording one way, right and left, flip the tape over, and they interleave so you can still run two directions. Now on cassette tapes, we'll talk about them in a moment, but they simply put the left and right together. Why they did this way and cassettes the other way, I don't really understand. I've never looked into it. May have been an important engineering decision. Maybe someone just thought it would be better. But that's the way a stereo recording is made on reel-to-reel tape. But on a cassette tape, they simply put the tracks right next to each other here. So here's the face of the tape, and we had our two heads. Now, of course, these are a single head with two recording heads or playback heads in one. And so on your cassette tape, we've had our tracks together. So there's our right track, there's our left track. Flip the tape over, and there's our right track, and there's our left track. And so they're just recorded right next to each other. And of course, it's 1/8" tape instead of 1/4" tape. But that's the way that was recorded on the cassette. And since we're now talking about cassettes, let's talk about how cassette tapes worked. So here's a compact cassette. It's a self-contained cartridge with the tape in it, and it has holes in it to facilitate spindles that come through to move the tape reels. You could get some high-end cassette tapes that actually had little tiny reels in there. Most of them just used the shell of the plastic to keep the tape in place. But there were holes to facilitate the spindles to move the tape reels, and then in the front there were holes to facilitate the capstan, the pinch roller, and the record and erase heads and whatever. So let's take a look at that from the top. So we have our head, and inside the cassette is a little pressure pads, so they did not use hyperbolic heads. And so there's a head, and then there was an erase head, so there are two heads, erase and playback. And over here there's a third window which would accommodate the pinch roller, and a little hole here to accommodate the capstan which came through that. So here's a picture of the cassette, and so here's a hole for the erase head, a hole for the record and playback head, and then pinch roller, capstan, and you can see the mechanism in there. So now we flip the whole thing over. Now the hole that was for the capstan is now for the erase head, and this one stays the same, and now the hole that was for the erase head is now for the capstan and pinch roller. So it flips over to accommodate that. Some high-end systems had a combination record playback that actually had two separate gaps. So they had a record gap optimized for recording, a playback gap optimized for playback. So they're basically two heads in one, a complete magnetic ring with gap for record, a complete magnetic ring with gap for playback. And of course you could do the same thing here as with the reel-to-reel. You could monitor while you were recording. So this would be for high-end cassette recorders. Now I talked about the standard speeds for open reel recorders. They were 7.5 inches per second, 3 3/4 inches per second, and 1 7/8 inches per second. The standard speed for a cassette recorder was 1 7/8 inches per second. What problem is that going to give us? Yes, terrible high frequency response. So one thing we had to do with cassette recorders is have a very tiny gap in the record and playback head. And another problem with moving the tape so slowly that I didn't mention before was that it increases the tape noise. So we have more hissing sound on a cassette tape. So how do we mitigate these frequency response and hissing problems? On low-end systems, we didn't. But for high-end systems, we had some things we could do. So let's talk about the hissing problem first, because that was the first one addressed. And you may have heard of Dolby systems. Well, Dolby makes all sorts of high-end audio equipment, but they became famous in the early 1980s with the development of noise reduction systems. So for professional systems, they worked with multiple separated frequency ranges, but for home systems, it only worked for one frequency range, and that's what we'll talk about here. So what Dolby did is basically something very similar to what they did with vinyl records with the RIAA equalization. Dolby boosts the high frequencies, and so if you have a tape player that records in Dolby, you record it using the Dolby noise reduction, and when you played it back it sounded very tinny because they had boosted the high frequencies. But then you press the Dolby playback button, that reduces the high frequencies, which is where most of the hiss is, so that reduces the hiss, and since we recorded the high frequencies at a greater volume, that reduces them down to what sounds normal. So that got rid of a lot of the hiss, which was a perennial problem with cassette recorders. That system I just described is Dolby B. Dolby A was a multi-range system that worked on, I think, 4 different frequency ranges, maybe more, for professional systems. Now, as far as frequency response, to get a higher frequency response, we can make a smaller gap. But by changing the tape formulation and the bias, we could increase that frequency response a little bit, get up to maybe 17 kilohertz. So the first solution to that was chromium dioxide tape. So the tape was formulated with chromium dioxide rather than ferric oxide. There may have been combinations. I know that there was reel-to-reel tape that was called ferrichrome. It was a rust layer basically with chromium dioxide on top. I never used it, and I don't remember if you needed a special bias. But for the cassette recorder, if you used your chromium dioxide tape, you had to increase your bias. So you had a different bias level because the tape saturated at a higher level. So you increased that bias on recording. You didn't have to do anything on playback, but increase the bias on recording, and that would increase the dynamic range for one thing, because you could record louder parts along with softer parts, but it also improved the frequency response, and I'm not sure what mechanism did that, but chromium dioxide tape would give you better dynamic range and better frequency response, maybe up to about 17 kilohertz. And the last change was metal tape, where instead of using brushed iron oxide or chromium dioxide, they actually had metal particles, submicroscopic, tiny, tiny little particles of metal aligned along the direction of the tape. So we're kind of back to the wire recording where we're recording on pure metal. But with the proper bias, you could get even a better dynamic range and better frequency response with metal tape. So toward the end of the heyday of cassette recording, you could get cassette recorders that had 3 heads, and they had Dolby B, plus they would work with chromium dioxide tape. You had to remember to press that chromium dioxide or quote high bias button to work with chromium dioxide tape, but you only had to worry about it on the record. And then you could also get metal tape. So you had a choice of metal, high bias, or standard tape, depending on what you wanted to use for your cassette recorder. Now at this point I could talk about some of the nomenclature, such as how wide tapes were, what their speeds were, how big the reels were, how much time you could get out of them, but I don't think it's worth going through in the lecture. You can read that in the reading material at Vocademy. But a couple other things to talk about. One is just a little bit of terminology. So if you had a tape recorder, it was all self-contained. Plug in a microphone, talk into it, or plug another source into it, play it back on its own speaker, had its own amplifier and speaker. That was a tape recorder. But more common was the tape deck, which was a unit that would go in with a stereo component system where you had a tape deck and an amplifier and separate speakers, and the tape deck only had the electronics used to get the signal onto and off of the tape. It did not have the amplifier to play back. It would just give a line out signal for your receiver or your amplifier or whatever equipment you had in your component system. Some of the problems we had were wow. It's when the sound changes frequency slowly, and it could be very annoying. It could be caused by a number of different problems. Something inside where we have either some lubrication problems or something that's become eccentric, or any problem that causes the tape speed to vary as it goes across the head would cause what's called wow. That was not as common in tape recording as it was on turntables, where we had maybe a record that was pressed a little bit off center or something. Another problem though is flutter, which can happen if the tape is kind of sticking and releasing as it goes across the head. It'll cause a very fast change in frequency called flutter. And another problem was dropouts if there were flaws in the tape. So as the tape goes by its recording, it gets to a spot where the coding on the tape is not as it should be, and you get less recorded. It'll usually drop in volume and in frequency response. I actually had a CD recording of Beethoven's Ninth Symphony, a particular recording that I knew was excellent from the vinyl days, and I finally got the CD. And somewhere in the transfer process, they went from the master tape to an intermediate tape to the CD, and the intermediate tape had a dropout. Also, they had saturation. That was a terrible, terrible recording. I don't know. It was shortly after Sony took over Columbia. Absolutely horrid recording. It had dropouts and it had saturation where you could hear the distortion. And I knew the recording was originally good, and to certainly give a bad review on that particular recording. Then they released it with a combination of a couple of other things in a 2 CD set, and this one was perfect. So we have wow and flutter and dropouts are some problems we can have with the tape, and if you have those on your original tape and you take that to your CD, you end up with all those problems on your CDs. There are a few things I want to talk about before I go. So one is multi-channel recording. Of course, stereo recording is multi-channel, but I actually had two, count them, two 4-channel reel-to-reel recorders. And these, of course, used the same 4 tracks, but when you recorded, you could either do normal stereo with 2 tracks in one direction and the other 2 tracks in the other, but with the special 4-channel heads these decks had, I could record 4 channels at the same time on the tape. But of course I couldn't turn the tape over and go the opposite direction because I use all 4 tracks in one direction with 4-channel recording. And these from the factory had the option of doing 2-channel or 4-channel recording. I found it a fairly easy mod to go in and switch it so I could go 2 channels, the other 2 channels, or all 4 channels by just monkeying with the electronics inside. And back to compact cassettes, one thing I failed to mention is that they had little tabs on the back to prevent accidentally recording over a tape that you wanted to keep. So commercial tapes had 2 little square holes in the back, but if you bought unrecorded tapes, they had little tabs over these that you could break out to prevent recording over the tape. These actually prevented the record button from being pushed. So there was some mechanical things that went on when you pressed the record button, and with these tabs broken out, you could not press that record button. And right next to these holes, some were a little elongated because those were chromium dioxide tapes. So some players actually had sensors that could poke into here and sense automatically if you had a chromium dioxide tape. And metal tapes had a very similar thing as I'm pointing to right here. And one thing I didn't mention at all is the popularity of 8-track tape. This started out as 4-track cartridges. I'm using the word cartridge instead of cassette because they were used differently in the market. A cartridge would have a single reel of tape, and as you can see here, the tape is pulled from the center, goes past spaces for record and erase heads because they did have recorders that you could buy, but most of these were bought pre-recorded with music on them. But it pulls the tape from the center across the heads, and then each cartridge had its own internal pinch roller, so you could push this in from the front and it just mated with the capstan and was able to start pulling the tape through. So the only impetus to move the tape was actually the capstan and pinch roller, and pulling the tape off the center pulled the reel and pulled the used tape back onto the reel. Now this particular one here, if you look at where the tape comes off, it looks like there's a twist in the tape, but if you look closely, it may or may not be twisted. If it is, this is what's called a Mobius loop. I did not know of them having Mobius loops in 4-channel or 8-channel tapes, but it was certainly possible. What they did in this case is they coated both sides of the Mylar tape with recording material, and so as you can see, as it twists, when you run the tape through one time, you do one side, but then it flips over to the other side for the next time through. I know these existed for radio broadcasting where they had cartridges with either bumper music or commercials that the DJ could play over the radio, but I don't know that these ever existed for 4-track or 8-track consumer tapes like this one here. But if you look, it looks like it could be twisted. So it may be a Mobius loop or it may not. So with the twist, it's a Mobius loop. Without the twist, it's just a regular tape and can only play one side. A problem with the Mobius loop, though, with so much recording material right next to each other, is that it exacerbates another problem I didn't mention, which is print through. When we wind this tape up, we get one layer on top of the other, and the magnetic recording can actually transfer over to the next layer of tape. And so you might hear a faint echo of the sound on the tape as it goes by, and that is called print through. Would have been a bigger problem with a Mobius loop, but it's faint and most people might not even notice it. And I mentioned 4-channel cartridges. In the 1960s, the Lear Corporation of Learjet fame helped develop an 8-track system, which instead of the 4-track system where you used 2 tracks at a time for stereo recording and you had a total of 4 tracks, they had a total of 8 tracks. So the reporting card of the head was thinner. And to change tracks, it was actually mechanical. So the head did not have 8 loop and gap mechanisms in there, only 2. And to change tracks, it would actually physically move the head, so it would make a good loud kerchunk when it changed the position of the head. With the 4-track, it could only do 2 programs, so it plays the tape through once. And there was a little piece of metal tape that could be sensed by some contacts in the player to see when the tape was finished, and that would tell it to switch the heads and to go kerchunk to the next program. And if you had 4-track tape, you could have 2 programs, and if you had 8-track tape, you could have 4 programs, each stereo, or 8 separate tracks. And the head had actually only 2 pickups, but you could move it back and forth on the tape. A couple more things I want to talk about are, one, high-speed duplication. So in the heyday of commercial pre-recorded cassettes, they had machines that could run the master tape at a high speed and run the cassettes also at a high speed and record maybe at double speed and save time in the time it took to record. Of course, they'd have banks of recorders recording off the master tape, and they would have a technician in there who puts all the tapes in, runs it, duplicate maybe double speed. I don't know if they could go faster. And because both tapes were going at high speed, they would get a normal speed duplication. I don't know what downsides there were to this. I've heard that it affected the low frequency response, but I don't know what mechanism that would have been. And of course, high frequency response shouldn't have been a problem running the tape at high speed. So it worked because that's how they made commercial tapes. They didn't duplicate them in real time that I know of. Although it could have been done with a master tape and bank after bank of recorder. They had special machines that could record multiple cassettes at one time, and they could have done it in real time, but I know it was also done at high speed. And last but not least, I want to talk about the venerable volume unit, or VU meter, and these were used to monitor the level that was being recorded on the tape. And if you look at it, you see that we have a point near the top end called 0 dB, and to the left we have negative numbers, and to the right into the red we have positive numbers, and it goes up to plus 3 dB. And these were designed such that 0 dB was your saturation level. So your needles were over to the left, meaning low signal, and as you recorded louder and louder, they would tend to jump up more to the right. So your needles were constantly moving as you recorded. And the idea was to avoid harmonic distortion by going into saturation, which started at 0 dB. Now, I've talked to technicians recently who say that they meticulously keep the needle out of the red, but earlier, back in my day, it was the common practice, if I remember right, that if you wanted to have perfect fidelity that I could hear the difference of, you would keep those needles down below 0. But if you get into the red, you're still less than 3 dB of harmonic distortion, which most people can't hear. So if you want to make sure you get the highest level on the tape, you would go ahead and let that go into the red, just not peg the needle, and most people couldn't hear it. I'm not even sure I could, because 3 dB is the minimum that theoretically a human under normal health could hear. Funny thing is, if you are sick and have an ear infection, you might be more sensitive. So if you want to be safe, keep the needle under 0, But if you go into the red a little bit, you're probably not going to have noticeable distortion on your tape. And that's about all I have to say here, so let's go back to our regularly scheduled program. So I've just about covered everything I want to on this subject in this lecture. There's a little more, but not much in the reading material at Vocademy, just some statistics, basically how fast, how much time, and such on tape reels. So we're pretty much finished with what I want to say about analog audio recording. So if you found this useful and informative, please, as usual, give me a thumbs up. That really helps the channel. Be sure to subscribe. I'm coming up on 50,000 subscribers now, not half bad. When you subscribe, hit that gray bell so you get notified when I put up new videos. And if you want to learn electronics technology, perhaps become a certified electronics technician, or just get a jump start in your engineering, or just learn because you want to, you can go to vocademy.net and take my free course. And to help me put these videos online and keep Vocademy free, you can go to patreon.com/Vocademy and pledge your support. Or to make a one-time donation, go to paypal.me/voced, V-O-C-E-D. And as usual, a big thank you to my patrons and my one-time donors. Couldn't do this without you. And thanks to everyone for watching.